So this is B6.
Yes, so CMI 2023 B6.
Okay. Tell me the question.
So, sir, the setup is we start with an integer a1 greater than 1.
Okay.
And so what happens is if n plus 1,
Hmm.
so a n plus 1 is equal to,
Okay. If an plus 1 is equal to.
no, sir, the if is not there. Like that comes
Oh.
later. So it's like a piecewise. Yes, sir. An plus 1 is equal to square root an
Hmm.
if an is a perfect square.
Okay.
And if an is not a perfect square, it's equal to an plus 3.
Okay. An plus 3.
Yes, yes, sir.
Okay.
So now the question is, we define the trajectory of A1 as the set of all numbers generated uh, while playing this game. So they've called it a game.
Okay. So the trajectory is. All
Yes.
right.
And as an example, they've given a trajectory of 3
Hmm.
is the set containing 3, 6, and 9.
Okay.
So this is yes. So now the question is, we have to determine all an such that the trajectory is infinite. So it's an infinite set. So that is the main question.
Uh-huh.
But they gave a choice. They said if you wish, you could solve these partial credit questions. So I was thinking we could do the partial credit questions and then come back to this so that it'll be
Okay.
like
So
for
okay.
completeness.
Okay. So you said find all A1 for which the trajectory is infinite.
Yes, yes, sir.
Oh, okay. For which. Okay. So we'll come to that once again.
Yes, sir. So
Yeah.
the first partial credit question is
Okay.
prove that uh, find an infinite trajectory.
Okay.
Prove that there exists an infinite trajectory. And give an example. So like we have to explicitly find it.
Okay. So what
So
is that?
sir, for this, I was thinking any number that is what is that 2 mod 3, since it will never, and since we're adding only 3,
Hmm.
this what happens is, suppose we start with a1 is 2 mod 3, then a2 will also be 2 mod 3, a3 is also 2 mod 3, so it's invariant under the process.
But when you take square root.
So we don't take square root because 2 mod 3 is never a perfect square.
Okay. Perfect. Correct.
So anything like 5 or 7, all of these should work.
Perfect.
Oh, sorry,
Yeah.
not 7, 8, 8.
Right. Yeah. So that's a good one. So anything 2 mod 3 implies infinite trajectory.
Yes. So that is one partial credit. And second partial credit question was for any k, for any natural number k greater than or equal to 3,
Right. Just
prove
one
that
second.
there exists. Yes.
Yeah. Implies T is infinite. Okay. And okay, what is the other thing?
So the other question is for any natural number k greater than or equal to 3, prove that there exists a trajectory of cardinality k.
Okay. So how do you do it?
Yes, sir. So for this one, I was thinking of like explicitly constructing it. So we already have 369.
Hmm.
So what happens is, suppose we take 36 as A1, then A2 will be 6.
Okay. So you take
Uh,
A1 as 36, A2 is
yes,
6. Okay.
A3 is 9,
Right.
A4 is 3.
Okay. So in this way, or you can
And
construct any trajectory, any size
yes,
trajectory.
yes, sir.
This is simple. Correct.
Right.
I understand.
So that is, yes, sir.
Yeah. This is also simple.
Uh, and the next one is prove that there is no trajectory of cardinality 1 or 2.
Okay. So, but how do we write this thing that there are trajectories of all sizes?
So
So
we start with A1 is 36 to the power uh,
that's right. I
2
understand that.
power k.
I understand. I
Yes.
just want to express the fact. Right? So how do you express the fact?
Oh, for all k belonging to 3, 4,
Yes.
yes,
Yes.
there
Yes.
exists
Yeah.
t
That I
such that
understand. Yeah. That I understand.
okay.
Yeah. But I just want to say then that this function, which takes this to t of a1 equal to k, right? This function is
Yes,
surjective.
sir. Yes, sir.
Okay, I don't think it's any use, but yeah. Okay. So then what's the other
Okay.
part? Uh,
Prove
no
that there
trajectory
exists no trajectory with 1 or 2 cardinal.
with one or two. So that should also be simple, right?
Yes, sir.
So how do you do it? Cardinality one.
So for cardinality 1, we must have that A1 is equal to square root of A1. We cannot have A1 is equal to A1 plus 3. That is a contradiction.
So one
So
is
we
not
must have,
possible. Correct.
yes, because we are taking greater than
Hmm.
1.
Yeah.
And for 2, I think something similar, sir. If you take A1 comma A2,
Hmm.
I think we need to work this out, sir. I'm not sure. But I was able to prove it. So what we can have is A2 is equal to A1 plus 3. Yes, sir. And square root of this is equal to A1. Yes, sir.
Right.
So I
And
guess now
then
we can solve this.
right.
Yes.
Hmm.
So this will give
And
A1 is,
you will not get any integers, maybe.
yes. Yes, sir. You don't get integers.
Right. So it's not possible. That's very
Yes.
simple question. Okay.
Yes, sir. So these were the partial
Okay.
credit.
Okay. Right. Sorry. So then that basically means that this is not allowed. One and two. Yeah, is not
Yes.
allowed. Right.
Yes, sir.
Okay. So these are easy. So then how do you
Yes, sir.
say find all A1 for which trajectory is infinite?
So I'm not like I no idea, so but I'm thinking like mod 3. So I was thinking something like actually I don't know. So this find all trajectory for which it's infinite, this is actually IMO 2017. Same question.
Same question? Okay.
Yes, sir. It's worded differently, but it's the same thing.
Okay, okay. Wow. Okay. So let us see. So 2 mod 3 is certainly there. Apart from that, we
Yes.
should think
Oh, sorry, sir. Our trajectory is finite. Sorry. Yes, trajectory is finite. So
find
we
all
want to
A1.
find those.
Okay, for
Trajectory is
which is
finite.
okay, okay.
Yes. Yes.
Alright. So,
So 2 mod 3 is out of the question. So
right.
if we take something like 4 to 5, something like that. So it goes from 4 to 2, 5, 8. Yes, sir. 4 to start. This one will also be. Oh, no, sir. It goes to 2 because 4 is perfect square.
Right.
So this will also be infinite because 2.
Okay, right.
Sir, I think the answer is A1 should be congruent to 0 mod 3.
Okay. Can we at least prove that
So,
for zero?
okay. So suppose A1 is a perfect square, then
Okay.
its square root will also be 0 mod 3 and it will be less than A1.
Why will it be 0 mod 3? Oh, yeah, it will be.
Yes.
Right.
And it'll be less than A1 and okay.
Right. Yeah, then you can use induction.
Yes. Yes.
So
So I
if
was thinking somehow it'll come back to A1 or something.
uh, okay, if A1 is a perfect square, right. No, but I'm just saying that in this case you can simply use induction,
Yes. Yes, sir.
right? But yeah, you are thinking that where exactly will it come back? But that's not. So, okay, let's see. So if it's 9, then it yeah, then it will get 9. But no, but it won't always come back, right? Because it's
Yeah,
taking
it won't
on
come back to,
right.
yeah.
But
But
but it's
it will hit some square that is 3 mod, 0 mod 3. Like we can be guaranteed of that. If it
okay.
doesn't come back to A1, it will, uh, since it covers everything that is of the form 3k, like
Uh,
between root A1 and A1, like all numbers of the form 3k are covered. So it must hit a perfect square that is not A1 or A1 itself. So I was thinking
okay.
something like that.
So okay. So you think from A1, if you go to root A1, then
Yes, sir.
how will it hit some perfect square eventually?
Uh, okay, one second.
Yeah.
So A1 is a perfect square.
Hmm.
So if it hits A1, we're done. Uh,
Hmm. Right.
and if there is another perfect square less than A1, that is of the form that is 0 mod 3,
Hmm.
it will eventually come to that as well. Like so the first square,
Why?
because this we keep adding 3, so it covers all numbers that are of the form 0 mod 3. So like
Correct.
suppose we're at 6, it comes 9, 12, 15.
Correct.
So it
Correct.
covers all of them.
Correct.
So I was thinking maybe we could do something with that.
Right. But I think that also you can say by induction, right?
Yes. Yes, 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 sir.
Isn't it? So you say, yeah, A1 is there, then this is smaller one. And this, you know, by induction, you can assume that this hits a perfect square. So A1 hits a perfect square.
Yes.
So that is not a problem. So it's done. But if A1 is a perfect square, then we are done. What if A1 is not a perfect square? So then also it is not difficult, I think, right?
Yes, because again, eventually it'll hit a square, and then we can come back to our argument, taking
Exactly.
that square as A1.
Exactly, because you have proof for all squares already.
Yes,
Right.
yes, sir.
Yeah, I think that's easy then. So you do this and you keep doing this till you get a square, and that square will also be 0 mod 3. So by the square case, you are done. Right. So
Yes,
A1 is
yes.
0 mod 3 is done.
And 2 mod 3 is done. So now we have to deal with 1 mod 3.
One. Right. A1 is mod 3 implies T is fine. Now if A1 is congruent to 1, right, and it's not very hard to guess that A1 is 2 mod 3 is not working, and it's not hard to guess that 0 mod 3 will work. Right. We
Yes,
want to
yes,
show
sir.
that 1 mod 3 will not work. Is that right? Yes.
Yes, sir. And then
Right.
we'll be done.
Then we'll be done. Yes. I think 1 mod 3 should eventually lead to 2 mod 3 somewhere, right? And then
Yes, sir. Like even I'm observing that pattern. So if we
yes,
start with 7, we get to 16. So we come back to 4, we come back to 2, 2 mod 3.
you get to 16, right, and you eventually come back to 2. Okay. Right.
Yes.
So then you are basically saying that yeah, so basically we can assume that A1 is a perfect square, because in the process that's where you will go, right? So
Yes.
you can
Yes,
assume
sir.
that A1, right, the A1 is a perfect square. A1 is some k square, and this is obviously 1 mod 3.
Yes.
But
Okay.
then
Yes, sir.
right, but then you will take its square root. So if that is 2 mod 3, you are done, right? So
Yes.
if k is 2 mod 3, you are done. But what do you do if k is 1 mod 3? I mean, then it's trivial, right? Because I don't know, you can just use induction, right? Because there's a smaller
How?
number. Yeah, right.
Okay.
Because, but let's write it. Maybe yeah. So so there is A1, and there is a k minus 1 square, some numbers, and then there is a
Yes, sir.
k square, right? And this is the first square that k reaches, that k1 reaches, right? And then you look at k square, and then from k square you go to
Yes.
k, right?
Yes, sir. Okay.
And
Yes.
what can you say about k? K can be, where will k be?
Uh,
K will be less than a1, right?
yes, sir.
Right, certainly, right? Yeah, because a1, yeah,
Yes,
that is
yes.
easy, right? K is less than a1. Yeah, so k is less than a1, so you have induction in your hand.
Yes.
This means
Okay.
you have
Yes, sir.
induction with you, right? If k is 2 mod 3, you're done. If k is 1 mod 3, you apply induction.
Yeah.
Because 1 mod 3, so again we are back in the 1 mod 3 case, and you apply induction, so you're done.
Yes.
So
Yes, sir.
I think, yeah, it is not. Only maybe that
Yeah.
there are three different cases, like because one is relying on the other case, so some some people might get a little confused. I mean, like
Might
even
get confused.
during
Yes.
exam, like it maybe that's what you also got confused. It means so it's difficult
Yeah,
during exam.
I
Very
didn't.
uh,
Yeah, I didn't try this. I just did the partial credit, sir.
okay, then it is fine. Either way is
Yes.
fine. Okay, so this was one question, right? It's a good question.
Yes. Yes, sir.
There is this games of NIM, right? Game of NIM. They are also like this. They rely on
So
all
game
rely
of?
on NIM, NIM. You can check it out.
Oh,
You can check it out from any basic book even to begin with, like mathematical circles. It's not a bad idea to do problems from there. Yeah, it actually teaches
yes,
you a
yes.
lot.
Yes, sir.
And then you can move on to other. Anyways, so then let us try something else.
Yes, sir. So maybe we could try ISI. There was
ISI,
B7,
B7. Okay, so
UGB7.
yes, but can we take can we take a 5 minutes break maybe? I think then we can.
Yes, yes, sir.
Yeah,
Yes, sir.
let's do that. So
Okay, sir.
let's join in five
So I'll
minutes.
leave the meeting, sir. Yes,
Yes,
yes.
join.